All right. Well, it looks like we have a very good group of people on right now, and it is now 11 a.m. Central here in Wisconsin. So hello and welcome to the first Sharon-Cutwell webinar. Imagine if your cutting tools could talk to you. You'll be able to accurately track drill quality, receive alerts when imperfections or tooling damage is detected, and precisely calculate the true lifetime of tooling, saving your company time, material loss, and money. It's called intelligent tooling, and it's one of the things Sharon-Cutwell is working on in its state-of-the-art process development center. Today, Sharon-Cutwell's Jeff Prom, Scott Prom, and Stefan Finster will be giving you a behind-the-scenes look at the Process Development Center and talk about what it can do for your tooling. One thing before we start, we'll be covering a lot of ground today, and we know you're going to have some questions. We will answer as many as we can during the Q&A portion following the presentation. You can submit a question at any time. Just click Q&A or chat at the bottom of the screen, and we'll get to them at the end. All right. Let's get started, guys. Take it away.
All right. Thank you, Eric. And thank you all for joining us on this webinar. As Eric said, I'm Jeff Prom. I'm the owner and president of Sharon-Cutwell Company. Also with us are Scott Prom, the Director of Technology and Innovation, and Stefan Finster, our sales manager. So we'll be talking today about our Process Development Center, or our PDC, as we like to call it. Essentially, it is our internally developed R&D center that we've been working hard at for the last 3 years. And so I'll give you the background understanding of what it is and what we do with it. And then really a few things that are really born out of that. And then is this concept of intelligent process development, which is really things that we're doing in there. And then ultimately intelligent tooling we'll touch on slightly as well. We're finishing today with a couple of case studies, examples of showing you how we've used this out in the real world. We've got an automotive case study and some aerospace case study and development studies that we'll talk about as well. And we'll finish with some Q&A. So that being said, what is our Process Development Center? Essentially what we like to say, why we have it, why we're doing it, why we're using it is it's our tool to drive innovation and process improvements, whether it's into our customers' processes or into our own internal development. So what is it physically? It's a testing and development center that's built with the latest machining equipment, measurement and analysis equipment, and it's fully staffed with dedicated personnel to carry this out. We have we bought two brand new machining centers for this. One of them is outfitted with MQL, minimum quantity lubrication, and one of them is outfitted with high pressure coolant, so we can kind of attack all the different types of processes that are commonplace in industry today. We have surrounding it a lot of force and measurement equipment, analysis equipment, measurement and analysis equipment. We utilize extensively ProMicron spike unit for force measurements and analysis, and we'll talk about that. Alicona, which is an advanced inspection and wear analysis tool. We utilize high-speed video to get detailed process visualization, as well as a host of other equipment. And as I said, we have dedicated personnel just to our Process Development Center. This is just a kind of a pictorial view of what it is, and these are the machines that we have set up to perform the testing. Here's the Spike mobile unit, which is what we use from ProMicron, which is our force sensing unit. This gives us our force data, and this is our Alicona for the detailed measurement. We do edge measurements, we do surface finish, we do a lot of measurement with the Alicona. And then, of course, we have kind of Scott, who's in charge of bringing it all together. So why does it exist? Really, again, as I said, to drive innovation as a means to drive innovation and process improvements into our customers' applications and their processes. It's a tool that really is there to help solve the more challenging hole making and machining problems that we find in industry. So what is the need? Why did this come to be? We found that there was largely an unmet need out there to solve these types of problems, and to bring advancements into our customers in a timely manner, and to do so in a non-production environment. And I'll talk a little bit more about that in the next slide. And really no one is doing this, at least not to the intimate level that we are, where we are in very close contact with the engineers who have the needs, and giving them an outlet to really get those solved in an organized manner. So just a little background on what, the kind of the methods of process development that are in use today. And I'll say that the most common method that we see our customers use is one that in our opinion limits advancements, limits the ability to bring advanced processes into their environments. And so the common method is we see our customers bring tried and true solutions, things that they know they use and they can trust. And they bring old solutions into new projects, and they need to do that because they need to minimize risk. They need to know that when they bid something, they need to know that it's going to work. And so many times they're based on lots of experience, and that's true and that's great, but the ability to take risk is relatively limited. Because if they wanted to bring a new solution in, and it has to be tested on the floor, and that will involve risk. There's uncertainties with doing something new and different. Many times it disrupts production, especially if it's a process improvement on an existing project. It'll be disruptive to current production. And even if it's a new project, and if it's uncertain, they're not sure if it's going to work. So these are all factors that kind of make people hesitant to bring new ideas in. And it's an inherently slow process. When we are involved with this type of process, we may give a new solution or a new design to a customer. They'll test it in their environment, and invariably we'll need to tweak it. And then so the tools have to come back to us, and we may make some changes, goes back to them, and they have to find time to run it again. And it's just an inherently slow process. And in general, the decisions that come out of it are driven on minimal amounts of data relative to the amount of data that we can gather within our environment. So what is the PDC method? Well, it is one that we believe enables advancements. It doesn't limit it, but enables advancements, because we are able to test and optimize processes offline. We are not disruptive to our customers' environments. We have a tremendous amount of data that we are using to make these decisions with on the various inspection and analyzation equipment that we have. And we allow for really rapid solutions. We will design a tool, manufacture it, test it, and as we decide we need to tweak it, we can literally, and at times we literally walk over to our grinding machines, make adjustments on the tools, come right back to the measurement, our test equipment, and rerun tests. So this allows for a very rapid iteration of solution development. And we can take risks, and risks. In fact, we embrace risks, and in our environment, we don't mind breaking a tool. We need to push things to find out where the limits are. Commonly we look at trying to fail forward. We learn as much from things that don't work as things that do work. So we have the ability and desire to take risks to learn. So in the end, we are bringing a mostly baked, optimized solution to our customers, right to their spindle. It's not all the way there, because admittedly our environment is not exactly the same. We do our best to mimic their environment, but if we can get an 80% baked solution to our customer, generally that last 20% to get there is really relatively easy to do. Oops, wrong way. So what do we do in our PDC? Just kind of summarizing it. Essentially, we learn. It's a process. It's a systematized process that allows us to learn. We help solve our customers' problems. We co-develop solutions many times with our customers who are doing development. We may be doing some development to augment their development, or vice versa. We share information, and ultimately create an optimal process with our customers. We certainly develop our own products. We have internal projects that we're constantly working on to develop and optimize and grow our own product offerings. Another important thing we do is we collaborate with industry partners. So people who are on our side selling and bringing solutions to the customers that have complementary technology. And we'll be talking a little bit more about the ProMicron spike unit. We work with another company, Midis, where we really are collaborating with partners to help bring the best solutions collectively to the industry. So now just shifting gears a little bit. So out of the PDC, out of the Process Development Center, we have this concept of intelligent process development. So what is that? It's really taking all of these tools, these measurement tools, the resources we have and our expertise to create an objective understanding of the drilling process. So again, it's a data-based understanding of what is really going on in the drilling or a machining process. So it's like trying to take the veil off of what's going on inside of a hole. And you'll see a little bit more about that. And then we use that understanding to guide our tool geometry and to really guide process variations that we will try, essentially then to create desired outcomes. So how do we do that? Again, I'll just give a few examples of how we utilize the spike unit, which is a force measurement analysis tool, the Aerospace, which is our inspection and wear analysis, and high-speed video that gives us detailed process visualization. So I'll just show a few examples of that. Again, this is the Spike Mobile, and on the right, you'll see it. This is a typical setup for us where we're getting bending, thrust, and torque data, Bluetooth back to in real time to a computer. This is the output that we're getting. This is a typical example of a full life test that we've done on a carbon fiber and aluminum stack, a typical aerospace stack of material. Here we drilled in excess of 700 holes, and you see the peak thrust values for both the carbon fiber and the aluminum. So we can see how it's traversing over the course of its tool life. Here's a more detailed look. We can drill down and many times do to look at just a detailed single hole that we drilled. Here's an example of, again, an aerospace application where we did a drill and countersink of one hole in carbon fiber. So this entire process took 2 or 3 seconds, and we have it broken down literally to the millisecond, where we are seeing everything that is going on at a millisecond level within the drilling process. In this particular case, we had a vibration event occurring. We knew somewhere in the process, so we could use this data to see exactly where it was occurring and how long it was occurring. So to give us that level of insight as to what is going on inside the hole at any given time is a very powerful tool, very powerful diagnosis tool for us to help solve problems. How do we use the Aerospace? And this is one example where we will on most of our tests, we will monitor wear of our tools. This is a case where, again, this was drilling in carbon fiber, and we monitored the wear at a key wear hotspot on the tool. So every 100 holes, we would take a detailed picture of the tool to see exactly what is happening over the course of the wear of the tool. We can actually overlay these, and you can literally see a kind of an animated view of tools wearing with this tool as well. This is an example of what we use high-speed video for. In this particular case, this is an example where in aerospace, a common application where you have to drill out a temporary fastener, a tack drill. Here's where we're drilling out this tack drill. Again, this is using a VAD process, a vibration-assisted drilling process. We're working with our friends from Midis on this, and we are here in this case. There was some chipping going on, so we wanted to see what was happening as we were drilling out the back of this tack drill to see if we could identify exactly where the chipping was occurring. So this drill is rotating at over 4,000 RPM, and so it gives us a very clean, detailed view as to what is going on inside the cut. There's another little video. It's kind of a fun one. We call it bend to break. And this is a case where we purposefully set up an unstable carbon fiber panel that is unsupported. So as we're drilling this with one of our wave-point drills, and you can see the panel is going down, and eventually it pushes it down, probably almost a 1/4 inch. And we're seeing what happens as you drill into unsupported material, which is common to do in an aerospace application. So as it breaks through, the springboard, the solid carbide drill did not like the springboard effect, but it gives us the ability to see these kinds of things. Again, this drill was spinning at 6,000 RPM, so we get a very clean and close view of it. Last thing I want to talk about is intelligent tooling. So this is kind of taking this intelligent process development to kind of another level. And what is it? Essentially, it's this concept that the tool can communicate in real time back to an operator, back to a machine, its current health and status. So we utilize, primarily in this case, we're utilizing the spike unit, and we use this a lot during our R&D process and in troubleshooting. And so we're constantly monitoring force plot data in real time as the tool is evolving through its life. So we get to see what is going on. So the tool is essentially giving us this data we otherwise wouldn't have to know exactly what is going on. Allows us to observe the wear patterns on the tool to get predictive tool life. We can also see, and Scott will show you later, we can see where we have an abnormal event might occur. So we can watch the data and see that an abnormal event may have occurred where we're still drilling holes, but something has happened. So it allows us to do this real time. Where this is really leading to, and we're working closely with ProMicron, and they certainly are doing a lot of this, our future state is where we can allow the tool to be predictive and essentially really talk to the operator, talk to the machine, and say that there is a problem. So the way we do that is we can create all the data set profiles of what is considered good and normal wear, and we send that data to ProMicron. We can also create data files of abnormal wear. So we know what the condition may be. And again, Scott will show you some of that. So we have known abnormal conditions, but we can create data set patterns of what abnormal is. And then the smart people at ProMicron they will create algorithms and KPIs that will essentially be able to predict or tell an operator what has gone on with the tool or what is going on with the tool. And so you can do this to really maximize tool life. If you have a nice normal pattern, but you no longer have to set a number of holes or number of cycles. You basically let the drill run to its entire life every time. So you get 100% of the tool life out of it. So it'll give you 10 to 20% more in tool life because you don't have to back it off. And it also, and probably even more importantly, it minimizes scrap. So a lot of scrap occurs because you still may be drilling holes and you don't realize you're drilling bad holes. So in this case, it can give us a predictive model that says that the tool is not happy, and it can tell that. So that's kind of the concepts that I want to go over, the PDC and the intelligent tooling. Now we're going to talk a little bit, Stefan is going to talk a little bit about some examples where we've used this out in industry. In this case, he'll talk about an automotive case study that we worked on.
All right, thanks, Jeff. Hello, everybody. So we had an opportunity last year. One of our automotive manufacturer reps brought us an opportunity from one of the big three automotive manufacturers in one of their engine block production plants. And they were having a problem with B-axis faults due to high thrust. They were getting a lot of machine alarms and shutting the machines down, and in turn shutting the entire assembly line down. So with all the delays, we had been told it was about 30% downtime in an average week. So it was getting a lot of attention. This is in a cell that was supposed to kick out about 160,000 blocks, engine blocks last year. So very high volume application, and looking for quite a bit of help. Next slide, Jeff. So they came to us with a project, and after some internal review and working with the customer, we decided it should be a good fit for us as something to tackle. We've certainly been familiar with cast iron and ductile iron drilling over the years. So we brought in customers' parts. They gave us a full-on engine block as a sample, as well as they provided some test coupons, some cast iron Durabar coupons for us to drill into. So they kind of spec'd out the casting that they thought was as close as possible to the actual engine block. So, and they also provided some incumbent drills for us to do some baseline testing. So after that, we picked, after some design review, we picked 3 different designs for us to manufacture and do some testing with. So 3 different geometries. And Jeff, why don't you go next slide? So after we went through and did our designs, we did some baseline drill testing, and then with their incumbent drill, and used the spike unit from Pro Micron for gathering that thrust data that they were claiming was showing, faulting out the machines. And after running through all 3 of our designs and running different speeds and feeds, gathering the data on all the different speeds and feeds for all the designs, we did notice some very dramatic improvements in the thrust. So one thing to note was, as we went through our different designs with different geometries and different hones, different edge preps, we noticed that when we increased the feed rate, we did not the thrust didn't go up with the feed rate. So we were able to actually increase the feed and keep the thrust at a much lower rate. So after in total, it was about a 6-week project. So Jeff, I think you had on the last slide, if you don't mind going back, just so I can kind of reemphasize. So they gave us, we kicked off the project in March of last year, and go ahead. And then by May 6th, so about 6 weeks, we had drills tested and the baselines and drills tested, and we had a fully, a full solution to propose, and a drill design ready for them to take into their production and do their own testing. So after looking at our data and with the information we gave them, with some slides similar to this one, they were very interested in getting into their production machines. So they ordered a couple drills for testing on their actual production horizontal machines in the cell, and they were able to successfully replicate all the feed rates, and the B-axis alarms, did not come back. So the thrust correlation we had was very accurate for what they were doing, and certainly they enjoyed the increased feed rate as well. So we actually a very positive byproduct was the increased feed and increased throughput on this one drill. So they've since purchased the production drills now, so we're in production on that cell, and then we're also on the same block. We're looking at about 4 more drills, kind of doing the same thing, trying to increase feed, and also as a byproduct tool life as well. So that's all I got, Jeff.
Thank you. Thanks, Stefan. So next, we're going to talk a little bit about a little bit of how we utilize the PDC in our aerospace development. Just by way of background, many of you know that we have our patented wave-point design that we've used a lot in aerospace. In general, we have we call our P2 version, which is used in composite only, a P3 version that's used in composite aluminum stacks, and a P4 that's used in composite titanium stacks. And it's an ongoing development work that Scott will talk to you about a little bit more. This is just a video, an interesting video that again, high-speed video that shows one of our drills exiting material. This drill is spinning at 6,000 RPM, and so it gives you a real detailed look of what ends up being a very clean and clear exit, and at a level that that is informative to help us understand what is going on and how we can continue to optimize. So with that, I will let Scott talk about a couple of ways he utilizes our PDC to advance our wave-point technology.
All right. Yeah. So I'd like to just describe and walk you through just 2 little case studies that we have here that we've done in aerospace. and show you some of the results and some of the force data that we collect. So this first one, we did this was about a year and a half ago, 2 years ago, when we really started getting the idea of intelligent tooling. And so this one is a relatively simple test we did, carbon fiber only. And we had 4 drills at different states in their drill life. Drill 1 was a new drill. Drill 2 had a couple 100 inches of carbon fiber drilled on it. Drill 3 had a single chipped edge, a wave point. And drill 4, we found a drill that had 2 chips. So this was the worst case drill. And the question was, what do the force plots look like for these drills? So this first slide here shows a thrust comparison. We drilled 4 holes in a row. Again, 1/2-inch carbon fiber, continuous drill. And this clearly shows that drill number 4 with 2 chipped edges had a significantly higher thrust. Drills 1, 2, and 3 all had slightly different peak thrusts, but this again, one piece of the puzzle. Torque comparison, same 4 drills. When you look at that data alone, peak torque, not as much difference. So this particular parameter, you can kind of conclude, doesn't offer as much information on the health of the process. And now we have bending. Bending actually is measured in X and Y. And that is really key, because as we dig into this more, we really do extract a lot of information out of the bending. In particular, when we know it's an X and Y axis, we monitor that. So for this is the net bending on the drill, and you can clearly see that drill number 4 with the 2 chipped edges had arguably a tough time entering into the hole. There's a peak bending there before it gets settled in. So this was, again, early on, as we were getting into intelligent tooling, trying to understand, what is the differences? Can we measure differences? Next big question, of course, is what do you do with this data? So this case study, I'll call it number 2. So this is one where we started digging in a little more. So this was a more typical aerospace process, carbon fiber over aluminum. And what we did here is we took 2 of the same drills, identical drills. One we ran all the way to drill life, drill end, which was about 700 holes. And we'll call it the baseline drill, drill number 1. And we recorded data for the hole, for each hole. And I'll show that on the next slide. Drill number 2, what we did on that one is we induced a chip at hole 328. So it was, drill was going along well, then we took it out of the holder and we put that big chip in there and then continued on for the rest of the drill life test. Again, the goal is to look at what differences in forces can we pick up. This is just an example of a single hole. Again, carbon fiber, if you start on the left, this shows bending, thrust, and torque. Carbon fiber continuous drilling, and then we did 10 PEC cycles. So this is a lot of data. And that's one hole. We've got it for 800 holes. What I'm showing here, so this is torque versus the peak aluminum torque for these 2 drills. For drill number 1, the baseline drill, that's circled in green. And what you can see there is the torque, peak torque increases pretty consistently from hole 1 up until the hole 700 and 740. In the yellow, drill number 2, for this drill at hole 328, we took it out and chipped it. And there you can see for this one parameter, peak torque in the aluminum, that jumped. We identified that. I'm just showing this as this is just one example of the type of the detailed look that we can get with all the force data. Again, bending X and Y, we get something called the spike polar plots. And And there's a lot more to look into and to try and learn what's going on. So we are working on that. Our future state, hopefully, is to take all this data and again, be able to predict the health even better. We're in the early phases of this, but we're very optimistic, and we think that this has got a good future. So that's all I have for the moment.
Thank you, Scott. So that's kind of the balance of the things we wanted to cover. I guess I just again want to thank you for joining up and listening in and learning about our PDC and the things that are going on and what we're really trying to do to advance advanced drilling processes, but really bring solutions to industry, bring solutions to our customers. So what can it do for you? Again, we're looking for challenging applications to help you solve problems, and so we need to know what the problems are, so we're solving the right ones. And in general, we try to stay very close to our customers and close to the engineers, so we can really help them solve what they need solved. We do a lot of validating of speeds and feeds in tool lives. So it's very common for us to again give hard data to our customers. The bottom line is, again, we are here to drive innovation. The PDC is really about driving innovation into processes and giving a tool that allows it to happen in an environment that allows us to take some risks and be less disruptive of our customers' production. So yeah, that's all I've got. So we'll hand it back to Eric and we'll kind of move into Q&A.
All right. Thank you so much, guys. Very informative. Okay, so we're going to start the Q&A portion of today's event. If you have a question, please post it in chat or Q&A. We'll get to as many of them as possible. We also understand that many of you will have questions you don't want answered in a public forum. We will be sending out a link to a recording of this webinar to all of you. And in that email, we will also have a special link you can use to request an individual review of your projects or to receive more information about the PDC capabilities. All right, so we've got a few questions that have come in. The first one, what kind of projects are ideal for the PDC?
Okay, I'll take that. I mean, really, as I said, ultimately, we are here to try and solve problems that industry and that our customers are seeing. I mean, ultimately, we're trying to bring new solutions into production. So while it is pure R&D, we really have a customer focus and a production focus. So it's the best kinds of projects are one where either it's something that maybe you're in a competitive situation and you're having a hard time getting to where you need to be, or you're just up against some kind of challenge for some current or future production item. Obviously, we are in the business of selling special cutting tools, selling solutions. So something where we can help you create a better solution, and ultimately provide you with the tools that can do that. So it's something that is challenging. And again, we've helped, a lot of times we talk to customers and either many times they quoted a project and they're coming up 20% short. So we'll come in and try and help to get them that last 20 or better, or we work a lot with machine tool builders. And so if they're doing some kind of a turnkey application, they know they're coming up short for what their customer needs. So they'll bring us in to kind of help them get there. And then we will do then development work and testing to bring a semi-proven solution to them. So.
Yeah. All right. Okay. We've got another question, and this is about the Aerospace case study 2. The question is, was this a single drill application, or were there multiple tests that showed similar results when the one flute was purposefully damaged and the drill life was unaffected?
Okay, I'll take that one. Looks like I'm back. I just did a reboot. So
all right, improvise.
So to answer that, we've we've run, I've got probably, 10 to 12 drill life tests where we've captured all of that detail data. So while I just showed you 2 drills, the answer is I've got, I know I'm up to 11 at least, case studies, drill life data collections that we are looking at in detail. We have at least 2 or 3 the same baseline drills. Then we did at least 2 chippings already, and we got a little different results. So we continue to run more, and we plan on it to gather the data to make sure that when we do get these intelligent tooling out there, it needs to be robust. We get that, and so we've got a ways to go.
Okay, all right. We have another question here. I have an upcoming project. Can you help me create a process? And if so, what does that look like?
Yeah, we do a lot of process development. So yes, we provide cutting tools, but really one of the outcomes of this is it's a cutting tool with a process. And in many times, in fact, that to get the most out of the tool, it needs to be run a certain way. So because we have the ability to do testing, and obviously we have a lot of expertise and baseline in knowing where to start, we will develop, we will give with the tool recommended speeds and feeds to really maximize that tool life. And so, coming with the tool will come a process. And in case we highly recommend, you allowing us to do that so that you get the most out of it. And most of the time we can end up, pushing it harder than what you might think. But yes, it is a tool and a process that we will provide.
Okay, all right, super. We do have one more question. If you guys have any additional questions, remember you can post them in chat or in the Q&A. This one, it's kind of similar to the last one. What is the PDC process and how long does it take?
Scott, answer that.
Okay. So one of the things we've done is we came up with a standard workflow for when we go into the PDC. This just gives us some guidance. And the standard workflow starts with planning. In the planning phase, we work closely with the customer to make sure we understand what exactly do they want. What is the requirements and which problem are you trying to solve? So we get agreement on that, and we move into the next phase would be a tool design and manufacture, and we would get the materials that we need. Next step is we do the test, we execute it, and lastly, there's always some analysis required, and then some data reporting. We always have a test report. So kind of four chunks of time. How long does it take? That all depends on the complexity of the project, whether it's a simple one where they've got one drill diameter with one material stack. Those can be pretty quick, less than a week once we get in the schedule. If it's more complex, the project, the cast iron project, we ended up, you make different drills, you have a bigger test matrix. Those can take a couple weeks.
Okay, super. Thank you, Scott, and thank you, Jeff. And being that there are no last-minute buzzer questions here, we're going to give you guys 20 minutes of your time back today. So thank you all for attending. Again, watch for the recap email with a special link to request an individual review of your project or receive more information about our PDC capabilities. And remember, you can always get more information about Sharon-Cutwell anytime online at cutwell.com. Thank you, everyone, for coming. Thank you to you guys for sharing your knowledge today. This has been very informative.
Thanks, Eric.
Thanks for coming.
Okay, everybody.